Let's take a peek at this interval. Now, clearly it's an improper integral because the function in the Lagrange position is indeed not continuous over the entire closed interval from -1 to 1, in particular at x equals 0. Now, if you take a peek at what you learned from the past, to evaluate this integral, as x ranges here to here, if that function f is an odd function, and my function here is an odd function, then the evaluation is going to be 0 for the obvious reasons you get cancellation of area. But that's only if the second fundamental theorem of calculus applies. That's only if this function f is continuous over this interval. And in my example, I'm not guaranteed that it's 0. It could be, but I'm not guaranteed. So let's go back to what I said earlier. Since at x equals 0, I have a value of x for which this function is discontinuous over that interval, then let's go ahead and rewrite this as the interval from -1 to 0. And then 0 to 1. Which gives me this. And if I can ascertain one or this other integral diverges, then the original integral diverges. So if you don't mind me pulling out a piece of scratch paper, let's take a peek at one of these. How about the second one? Everything's positive, makes it easier for me to compute. Natural log of 1 is 0, minus natural log of s. But of course, as x goes to 0 from the right-hand side, this thing right here decreases outbound. So its opposite is going to increase with outbound. That being the case, since this first improper integral, I misspoke, didn't I? Since the second improper integral diverges, then who cares about symmetry? That one there diverges. I only get cancellation of area if the area in question is finite, and it certainly was not in this example, however counterintuitive that might be.